Today we'll consider some more about linear transformations and prove a theorem about them. Let's begin. The set of all linear transformations from a vector space V to a vector space W is denoted by L of V comma W. This is of course defined only for two vector spaces over the same field F. Since they're not over the same field, you need to do more work. The sum of two linear transformations S and T in L of VW is the mapping defined by S plus T of X, which is equal to S of X plus T of X for any vector X in V. And this is itself clearly a linear transformation because S is and T is. So by definition, so then we see that S plus T is inside L of VW, which is an interesting fact to note. Next interesting fact, which will lead us somewhere, is that the scalar product of any element C in F can be multiplied by a linear transformation T from L VW for any linear transformation T in L of VW. We define this as Ct of X is equal to C times T of X for any vector X of V. And clearly, since T is a linear transformation, therefore simply scaling it up by C will still be a linear transformation. It'll obey the appropriate laws. We can now finally check that the distributive law holds for addition and scalar multiplication for transformations in the sense that you can do distributivity of multiplication and addition of vector spaces. Therefore, since we have distributivity, closure under addition, and scalar multiplication, we get that the set L of VW is another vector space over the field F. That is, the set of linear transformations act as vectors, where if you consider a single element in the set of linear transformations, you consider it as a vector in that vector space, and you can scale and add it to other vectors in the natural way you do with normal vectors, except in this case, these are linear transformations themselves. Next, we'll note that linear transformations are mappings from one space to another. So, as in the case of any mappings, we can form a composition of those two mappings. We write this composition ST for two linear transformations, and it's defined as ST of V is equal to S of T of V. This composition is also a linear transformation because S of T of V1 plus V2. We apply the definition is S of T of V1 plus V2 is S of T of V1 plus S plus T of V2. And then we simply apply the linearity of S to split this S onto both this term and this term. That's S of T of V1 plus S of T of V2. But remember, S of T of something is simply ST of that thing. So this is ST of V1 plus ST of V2. So we this operates over addition. So ST is linear, or it respects addition. And then we'll show that it respects multiplication in this sense. ST of AV is S of T of AV is S of A of T of V is equal to applying the linearity of S as A of S of T of V, which is A of ST of V. So we have that ST is also a linear transformation because it respects addition and scalar multiplication. Now I'll prove a theorem regarding compositions, and we'll show in particular a special kind of composition, namely that of the inverse. We say a linear transformation T from V to W between vector spaces V and W over field F is an isomorphism if and only if there's a linear transformation S from W to V such that ST from V to V and TS from W to W are the identity linear transformations. To break down a little bit, we're going to be considering the inverse operation. So that's where we get the idea of ST equals TS equal to I. Think about groups from our previous chapter, and we can see that T in some ways is the inverse of S when you have the group operation of composition. With that, we see that we're going to confirm this isomorphism. Because if we have inverse, we're going to show some facts about it that will lead us to apply our lemma about isomorphisms, that it needs to span and have zero kernel. So let's proceed with the proof. If T from V to W is an isomorphism of vector spaces, then T is surjective. So for any vector W in W, there will be a vector V in V such that T of V is equal to W. Standard definition of surjectivity. And we have it's injective, so V is uniquely determined and cannot be, and so it can be viewed as a function V of S of W. That is, since this operation always exists and V is uniquely determined since it's injective, we can just simply say to W associate back the element V, and that will be V is equal to S of W for any vector W in W. And thus we define a mapping S from W to V for which TS of W is equal to T of V, because S of W we define to be V is equal to T of V is equal to W. So TS is equal to the identity map. For any vector V in V, since W is equal to T of V, it follows that T of V is equal to W is equal to TS of W, and then we see that we can apply T on the left. So this is going to be equal to T of S of T of V. I'm sorry, not on the left, on the right, in that instead of w, we can write t of v, since we have t of v is equal to w, and then we simply pull it out by using the definition of composition, so it's equal to ts t of v. So, since we have t is injective, it is necessarily the case that v is equal to st of v. That is because you only have one defined thing. That is t of v, and then we have t of st of v. So st of v has to be whatever you put inside of v, because st is injective. I'm sorry, since t is injective. Therefore, since v is equal to st of v, st is equal to I. So we've proven that ts and st are both the identity maps on their respective things. We now need to show, we've simply created the association S, which associates to any vector w, the vector v, such that t of v is equal to w. We now need to show that S is a linear transformation. To do that, we're simply going to check the linearity conditions. Namely, if we have w1 is equal to t of v1 and w2 is equal to t of v2, then by linearity, we have w1 plus w2 is equal to t of v1 plus t of v2, and then we use the linearity to pull out the t, and we get t of v1 plus v2. So we associate to the vector w1 plus w2 the element v1 plus v2. That is, S of w1 plus w2 is equal to v1 plus v2. And v1 plus v2, by definition, are going to be S of w1 and S of w2 by considering this relation. And we'll note that if t of v is equal to w, then we can apply linearity. That is, t of av is equal to a of t of v is equal to a of w. So we apply the reverse. This statement, including this line, means S of aw is equal to av, but we remember we said S of w is equal to v, so we get a times S of w for any scalar a in F. So we have that it respects linearity, therefore it must be a linear transformation. Now let's do the reverse direction of this bijection. Let's conversely suppose that there is a linear transformation such that st is equal to I and ts is equal to I. Therefore, for any vector w in w, it follows that w is equal to ts of w, since ts is the identity map, so that w is in the image of t. Therefore, t is surjective, since we chose any w in w. If t of v is equal to 0 for any vector v in v, then v is equal to st of v, since st is the identity map. But we said that t of v was 0, so that's s of 0. And so then s of 0 is always 0 for any linear map. Therefore, we've shown that v equals 0, so that the kernel of t is the 0 vector. Hence, t is injective. This suffices for a proof, because we've shown that t is injective and surjective, therefore it's a bijection, therefore when you view it in terms of vector spaces, it's an isomorphism between v and w. Therefore, we have a reverse direction, namely that t is an isomorphism. With that, we're done, and we'll start with some more theorems next time. Thank you for watching.